Welcome to another episode of My Weird Prompts, an AI-generated podcast featuring the random prompts of Daniel Rosehill as answered by a revolving cast of friendly AI characters. Join us for deep dives into AI, technology, and whatever other random thing Daniel finds fascinating today. Subscribe on Spotify or your favorite podcatcher. Now, today's episode.
This episode was generated using artificial intelligence. Please verify facts.
Hi Herman and Corin. So for anyone who spends time downloading programs for Linux, downloading a distro for example, you'll often get to this big, huge selection of different download options that I think turns a lot of people off. They're just looking for that one button and suddenly you see, do you want to download the Turbo, the torrent, the ISO? Are you going to do it via USB stick, network installation? And then when you pick that, or you've asked ChatGPT which one do I want, and you think you're in the clear, then you get a list of options for different architectures. And you have the i386, AMD 64, and that should be, I think, enough for most people to get to the download link. You know it's AMD 64 if it's not legacy, and you're trying to put it on a desktop or on a laptop. But then you've got other ones like ARM64 used for Android and Raspberry Pi, if I'm not mistaken. And then beyond that, you've got these kind of slightly more obscure architectures that I sometimes see. And I'd love to understand a bit more about how these differ fundamentally. For example, when we're trying to get stuff on AMD 64 and getting it to run on a Raspberry Pi, it's not a simple process of just porting it. It's a very fundamental, it's called an architecture, right? So Herman and Corin, I've told you pretty much what I know. I'd love to understand the differences between these main monoliths of architectures. And beyond that, as I mentioned, the long list, you do see stuff like Solaris and stranger architectures that I think are often actually there for users running these things on supercomputers and things that aren't commonly encountered every day.
You ever find yourself on a download page for a piece of software, maybe a Linux distribution or a specialized forensic tool, and you are suddenly staring at a list that looks like a secret code? You just wanted a simple installer, something to get the job done, but instead, you're faced with a choice between i386, AMD 64, ARM 64, and maybe even some more obscure ones like Spark, MIPS, or PowerPC. It is one of those moments where the technical underbelly of our digital lives suddenly breaks through the surface, and if you do not know the code, it can be incredibly frustrating. You click the wrong one, wait 20 minutes for the download, and then get hit with a cryptic error message like, cannot execute binary file, or a total system freeze.
Herman Poppleberry here. It is like the digital version of going to a hardware store to find a replacement screw for a home project, only to realize there are 10 different thread types, 3 different head shapes, and some are measured in millimeters while others are in inches. Except in the world of computing, if you pick the wrong one, the software does not just fit poorly, it simply will not run at all. It is a fundamental mismatch at the most basic level of how the machine thinks. We are talking about the difference between a gasoline engine and an electric motor. You can have the best fuel in the world, but if the engine is not designed to combust it, you are not going anywhere.
Today's prompt from Daniel is about exactly this. He noticed that confusing array of options when downloading software or a Linux distro and wants to understand the fundamental differences between these architectures. He is also curious about why it is not a simple process to port software from one to another, like taking something from a standard desktop running AMD 64 and putting it on a Raspberry Pi. It seems like it should just be a matter of copy and paste. But as anyone who has tried to run a Windows game on a Mac knows, it is never that simple.
This is such a great topic because it forces us to look under the hood of what a computer actually is. We tend to think of software as this abstract, ethereal thing that just exists in the cloud. But software is ultimately a set of very physical instructions for a very specific piece of physical hardware. If the hardware does not speak the language those instructions are written in, nothing happens. It is the ultimate language barrier. And today, in February of 2026, that barrier is more relevant than ever because we are in the middle of a massive shift in the industry.
I think a good place to start is defining what we actually mean by architecture in this context. When we see those labels like AMD 64 or ARM, we are usually talking about the instruction set architecture, or ISA. Herman, how would you describe the ISA to someone who understands computers but has never had to care about the difference between a register and a bus?
The best way to think about an instruction set architecture is as a contract. It is the formal, legally binding agreement between the hardware designers, the people building the chips, and the software developers, the people writing the code. The ISA defines what the processor can actually do. It lists every single basic operation the chip is capable of performing. We are talking about the absolute primitives, things like adding two numbers, moving a piece of data from memory into a temporary storage spot called a register, or jumping to a different part of the program if a certain condition is met.
So it is like a vocabulary. If the ISA for one chip has the word for jump, but the other one only has the word for hop, the software needs to be rewritten to use the right terminology.
Exactly, but it goes even deeper than just vocabulary. It is also about the grammar and the physical layout of the information. It defines how many of those temporary storage spots, the registers, are available, how big they are, and how memory is addressed. If you write a program that expects 64-bit registers and you try to run it on a chip that only has 32-bit registers, the program is essentially trying to pour a gallon of water into a pint glass. It just does not work. The hardware literally lacks the physical wiring to hold that much data in a single thought.
Let us break down the most common ones people see. The big one for most of our lives has been x86. You often see it as i386 or i686 on download pages. That is the legacy of the Intel line, right?
Right. The x86 architecture is the absolute titan of the personal computer world. It started with the Intel 8086 processor back in the late 1970s. The i386 label specifically refers to the Intel 80386, which was the first 32-bit version of that architecture released in 1985. For decades, that was the standard. If you had a PC, it spoke x86. But as we needed to handle more memory and more complex calculations, we hit a wall with 32 bits. A 32-bit system can only address about 4 gigabytes of random access memory.
Which felt like an infinite amount of space in 1985. But today, 4 gigabytes is what you need just to open a few tabs in a modern web browser.
Precisely. This is where AMD 64 comes in, and the history here is actually a bit of a corporate drama. Intel tried to move to 64 bits with a completely new architecture called Itanium, or IA64. But Itanium was not backward compatible with the old 32-bit x86 software. It was a clean break design, which meant it was a nightmare for developers who would have had to rewrite everything from scratch. AMD saw an opening and created an extension to the existing x86 architecture that added 64-bit support while keeping the old instructions intact. It was called x86-64 or AMD 64. It was so successful and so much more practical than Itanium that Intel ended up licensing it back from AMD. That is why, even if you have a high-end Intel Core i9 processor in your laptop right now, the 64-bit version of Linux or Windows you download is almost certainly labeled AMD 64.
It is a bit of a branding irony that Intel users have to click a link named after their biggest rival. But then we have the new heavy hitter on the block, ARM. We see this as ARM 64 or AArch 64. This is what powers our phones, and more recently, the newer Apple laptops and the Raspberry Pi that Daniel mentioned. Why is ARM so fundamentally different from the x86 world?
This brings us to a classic divide in computer science, CISC versus RISC. x86 is what we call a complex instruction set computer, or CISC. The philosophy there is to have a huge vocabulary of very specific, powerful instructions. One single x86 instruction might tell the processor to go to memory, find a value, add it to another value, and save the result back to memory all in one go. It is very convenient for the programmer, but it makes the physical hardware very complex and power hungry because the chip has to have all the specialized circuitry to handle those complex, multi-step maneuvers.
And ARM takes the opposite approach, right? The reduced instruction set computer, or RISC.
Exactly. ARM is the king of RISC. The philosophy there is to have a very small, very simple vocabulary. Instead of one complex instruction, you might have three simple ones. Load the value from memory, add the value in the register, and then store the value back to memory. Because each instruction is so simple, the hardware can be much more efficient. It uses less power and generates less heat. This is why your smartphone can last all day on a relatively small battery, while an x86 laptop often needs a much bigger battery and a loud fan to keep the chip from melting itself. In the last few years, with Apple's M-series chips and now the Snapdragon X Elite chips in the Windows world, we are seeing ARM move from just being a mobile chip to being a serious contender for high-performance desktops.
So if the philosophies are that different, it makes sense why you cannot just run an AMD 64 program on an ARM chip. The ARM chip looks at those complex x86 instructions and has no idea what to do with them. It is like giving a set of IKEA furniture assembly instructions written in Swedish to someone who only speaks Japanese. Even if the end goal is the same, building a bookshelf, the steps to get there are completely unintelligible.
That is the perfect analogy. And this leads directly to Daniel's question about why porting is not simple. When you write a program in a high-level language like C++, Rust, or Python, you are writing in a human-readable format. But the computer cannot run that. It has to be compiled. The compiler is the translator that takes your human-readable code and turns it into the specific machine code, those ones and zeros that the specific architecture understands.
So if I have the source code, why can I not just hit a button that says compile for ARM instead of compile for x86? In theory, shouldn't the compiler handle all the heavy lifting?
In a perfect world, yes. And for very simple programs, it often is that easy. But real-world software is rarely a single isolated file. Most software depends on libraries, which are pre-written chunks of code that do things like draw windows on the screen, handle encrypted network connections, or process images. If you are porting your app to a Raspberry Pi, every single library your app uses also has to be available and compiled for ARM. If even one of those dependencies is missing or only exists for x86, your project grinds to a halt. This is what developers call dependency hell.
I also imagine there are hardware-specific assumptions baked into the code itself sometimes. If a developer wrote a piece of code that assumes the processor handles numbers in a certain way, or has a certain amount of cache memory, that code might break on a different architecture, even if it compiles successfully.
Oh, absolutely. One of the most famous headaches is something called Indianness. It sounds like something out of a fantasy novel, but it is basically the order in which a processor reads bytes. Some architectures, like x86, are little endian, meaning they store the least significant byte of a number first. Others, like the older PowerPC or some SPARC configurations, are big endian, storing the most significant byte first. If you move data between those two without being very careful, your numbers will look like complete gibberish. It is like one person reading a book from left to right and the other reading it from right to left. They are looking at the same characters, but the meaning is totally reversed. If your code assumes little endian and you move to a big endian system, your 100 might suddenly look like 16 million.
That sounds like a nightmare to debug. And then you have the operating system layer. Even if the processor architectures are the same, the way the software talks to the hardware is managed by the OS. So, running a program on ARM-based Linux is different from running it on ARM-based Windows or ARM-based Mac OS.
Right. You have the ISA at the bottom, then the hardware implementation, then the kernel of the operating system, and then the user space libraries. Porting software requires every single one of those layers to be compatible. When Daniel asks about porting from AMD 64 to a Raspberry Pi, he is not just asking about a change in the instruction set, he is often asking about a change in the entire ecosystem. The Raspberry Pi usually runs a version of Linux called Raspberry Pi OS, which is optimized specifically for that hardware. Even if you have the right architecture, you still need the right system calls, the way the program asks the OS to open a file or use the network.
It is interesting that Daniel mentioned Solaris as well. That is a bit of a blast from the past for many, but it still exists in certain enterprise environments. Usually, when you see Solaris on a download list, it is paired with the Spark architecture. That is another RISC architecture, but it was designed by Sun Microsystems for high-end servers.
Spark is a great example of an architecture that was built for a very specific purpose. It was designed to be incredibly stable and to handle massive amounts of data throughput in server farms. It has features like register windows, which is a clever way of making function calls faster by shifting which registers are visible to the processor. It is brilliant for a server, but it makes the hardware very expensive and specialized. You would never put a Spark chip in a laptop because it is not optimized for things like battery life or integrated graphics. It is a heavy-duty industrial engine.
This really highlights that these architectures are not just random choices, they are evolutionary responses to different needs. x86 evolved for general-purpose desktop computing, where backward compatibility was king. ARM evolved for mobile devices, where power efficiency was everything. Spark evolved for the data center, where reliability and throughput were the priorities. It is like looking at different species of animals that have adapted to different environments.
And we are seeing new species emerge even now. Have you been following the rise of RISC-V Par5 W5W5, C5 Type5, Corn? It is getting a lot of buzz in the technical community lately, especially as we move into 2026.
I have. It is an open standard architecture, right? Unlike ARM or x86, which are proprietary and require companies to pay massive licensing fees to use them, anyone can design and build a RISC-V chip for free.
That is exactly why it is so disruptive. Because it is an open standard, it is becoming a favorite for researchers, hobbyists, and companies in countries that want to avoid being dependent on Western technology, giants like Intel or ARM Holdings. It uses a very clean, modular RISC design. You can have a tiny, simple RISC-V chip for a smart light bulb, or you can add extensions to create a powerful RISC-V chip for a supercomputer. But because it is relatively new compared to the 40-year-old x86, we are right back to the porting problem. If you want to run Linux on a RISC-V board, developers have to go through that entire process of porting the kernel, the drivers, the libraries, and the applications all over again.
It feels like we are in a bit of a transition period. For a long time, it felt like the world was just going to be x86 forever. But now, with Apple moving their entire Mac line to ARM with their M-series chips, and servers increasingly moving to ARM for better power efficiency, like Amazon's Graviton chips, the monoculture is breaking up.
It is, and that is actually making software development more interesting, if a bit more complicated. We are seeing tools like Docker and containers become almost mandatory because they help manage those different environments. You can build a container that has all the right libraries and configurations for a specific architecture, which takes some of the sting out of the deployment process. It allows a developer to say, here is the ARM version of my app, and here is the x86 version, and the system can pull the right one automatically.
But even with Docker, you still usually need to build a different version of the container image for each architecture, right? You would have an AMD 64 image for your cloud server and an ARM 64 image for your edge devices.
Exactly. You are still dealing with the fundamental reality that the binary code, the compiled ones and zeros, is different. There is no magic wand that makes a piece of x86 machine code run natively on an ARM processor. However, we are getting better at emulation and translation. Apple's Rosetta 2 is a fantastic example. When they switched to ARM, they knew people still needed to run their old x86 apps. Rosetta 2 basically translates the x86 instructions into ARM instructions on the fly, or right before the first time the app runs.
It is impressively fast too. Most people do not even realize they are running translated code. But there is always a performance penalty, isn't there? You are essentially paying a translation tax in processing power to have that translator running in the background.
There is always a tax. Even with the best translation layer in the world, a program written and compiled natively for an architecture will almost always beat a translated version in terms of speed and efficiency. That is why, even if you can use emulation to run an x86 program on your Raspberry Pi using something like Box86 or Box64, it is never going to feel as snappy as a native ARM version. You are asking the CPU to do extra work just to understand what it is being asked to do.
So, if I am a user looking at that confusing list of download options, what is the practical takeaway? How do I make sure I am not downloading a paperweight?
The first thing is to know your machine. If you are on a standard Windows laptop or a Mac from before 2020, you are almost certainly looking for AMD 64, which is often just labeled as 64-bit or x86 64. If you are on a Mac with an M1, M2, or the newer M4 chips, you want ARM 64. And if you are working with a Raspberry Pi, you are also looking for ARM, though you have to be careful whether you need the 32-bit version for older models like the Pi 0 or the 64-bit version for the Pi 4 and Pi 5.
And if you see i38.6, that is generally for very old hardware, or for when you are running a 32-bit operating system for some specific legacy reason. It is becoming increasingly rare to need that for modern daily use. I think Ubuntu and many other major distros have officially dropped support for it as a primary architecture.
Right. Most modern Linux distributions are actually phasing out i386 because the hardware is just too old to be useful for most people. It is a bit like trying to find parts for a car from the 1960s. You can do it, but you have to go to a specialist. If you are downloading a modern web browser or a video editor, you almost certainly want the 64-bit version, which will be AMD 64 or ARM 64.
What about the more exotic ones? We mentioned Solaris and Spark. I occasionally see MIPS or PowerPC on lists for things like router firmware or old game console emulators.
Those are very specialized. PowerPC was the standard for Macs for a long time before they switched to Intel in 2006, and it is still used in some industrial applications and older servers. MIPS is another RISC architecture that was very popular in the 90s for workstations and gaming consoles like the Nintendo 64 and the PlayStation 1. Today, you mostly find it in embedded systems like network routers or some smart home devices. If you are downloading custom firmware for a router, you might see MIPS, but for a general-purpose computer, you can usually ignore those.
It is fascinating how these architectures become like archaeological layers in the software world. You can tell the age and the purpose of a system just by looking at what instruction set it uses. It is a map of our technological history, from the early days of the 32-bit revolution to the power-efficient mobile era.
It really is. And it is not just about history, it is about the future of how we interact with the physical world. As we move toward more specialized hardware, like AI accelerators or specialized chips for medical devices, we are going to see even more architectures. The dream of a single, universal language that every computer speaks is probably never going to happen because the physical constraints of different devices, size, heat, battery, speed, are too varied. A supercomputer and a smartwatch have such different needs that they will always need different brains.
That is a bit of a sobering thought for developers, but I suppose it also means there is always a need for people who understand how to bridge those gaps. The role of the compiler and the system architect is only going to become more important as the hardware landscape gets more diverse.
I think that is a great point. We are seeing a move toward higher-level abstractions like WebAssembly or WASM. It is designed to be a portable binary format that can run at near-native speed in a web browser, regardless of the underlying hardware. The idea there is that you compile your code to WebAssembly once, and then the browser's runtime, whether it is on an ARM phone or an x86 desktop, handles the translation to whatever architecture the device is actually using.
That feels like the ultimate goal, doesn't it? A way to write code once and have it run everywhere without the massive performance hit of traditional emulation. If we can get WebAssembly to work outside of the browser as a general-purpose runtime, that would solve a lot of the headaches Daniel is talking about.
We are already seeing that with things like WASI, the WebAssembly system interface. It is an effort to give WebAssembly access to system resources like files and networks, so it can run as a standalone application. It is still maturing, but it is a very promising path toward making the architecture of the processor matter less to the end user. Imagine a world where there is only one download button, and the software just figures it out.
Until then, though, we are stuck checking our system specs and making sure we click the right link. It is a small price to pay for the incredible diversity of computing power we have access to today. I mean, the fact that I can have a credit card-sized computer like a Raspberry Pi that can run a full desktop environment is only possible because we have these specialized architectures like ARM. if we tried to run a full x86 chip on a Pi, it would probably melt the board.
Exactly. If we forced everything to be x86, we would lose that efficiency and portability. The confusion on the download page is just the side effect of having the right tool for every job. It is a bit like complaining that there are too many types of shoes at the store. Sure, it is a little overwhelming, but you really do not want to go hiking in high heels or run a marathon in heavy work boots. Each architecture is a specialized tool for a specific environment.
That is a fair point, though I think the download pages could probably do a better job of explaining which shoe fits which foot. A little tooltip that says, if you bought your Mac after 2020, click here, would go a long way for the average user who doesn't know their AR64 from their elbow.
Oh, definitely. Some projects are getting better at that, using JavaScript to detect your browser and your operating system and highlighting the most likely download for you. But for Linux distros, where the users are often expected to have a bit more technical knowledge, they often just give you the raw list and expect you to know your way around. It is a bit of a rite of passage in the Linux world.
Which is why we have shows like this, I guess, to help decode the jargon. I feel like I have a much better handle on why my computer speaks AMD 64 and my phone speaks ARM, and why they struggle to understand each other without a good translator. It is all about the physical reality of the silicon.
It is all about the contract, Korn. The ISA is the foundation of everything we do with computers. Once you understand the contract, the rest of the complexity starts to make a lot more sense. It is not just random letters and numbers, it is the blueprint for the machine's mind. And as we move into the era of RISC-V and specialized AI silicon, that blueprint is only going to get more interesting.
I think we have covered the basics of the big architectures and the hurdles of porting. It is a deep rabbit hole, but hopefully this gives Daniel and our listeners a solid foothold. It is one of those things where the more you know, the more you realize how incredible it is that any of this works at all. The fact that we can send a file from an x86 machine to an ARM machine and have it look exactly the same is a miracle of engineering.
Every time I think about the billions of transistors on a chip, all following these precise instructions millions of times a second without a single mistake, it blows my mind. We are living in an era of technological miracles, even if those miracles sometimes come with a confusing download menu.
Very true. Before we wrap up, I want to mention that if you are enjoying these deep dives into the weird world of tech and prompts, we would really appreciate it if you could leave us a review on your podcast app or on Spotify. It genuinely helps other people find the show and keeps us going. We are aiming to hit some big milestones this year, and your support is the fuel for that.
Yeah, it really does make a huge difference. We love hearing from you all and knowing that these conversations are helping make the digital world a little less mysterious. If you have a specific technical term that has always bugged you, send it our way.
You can find us on Spotify, Apple Podcasts, and pretty much anywhere else you listen to your favorite shows. Also, check out our website at myweirdprompts.com for the full archive and a way to get in touch. If you have a question or a topic you want us to explore, send us an email at show@myweirdprompts.com.
Thanks to Daniel for sending in this prompt. It was a fun one to dig into. It is always good to go back to the fundamentals and remember that at the end of the day, it is all just ones and zeros being pushed through tiny gates.
Absolutely. This has been My Weird Prompts. Thanks for listening, and we will catch you in the next episode.
Goodbye, everyone. Stay curious.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to another episode of My Weird Prompts, an AI-generated podcast featuring Daniel Rosehill's AI prompts, as answered by a revolving cast of friendly AI characters including me, Cornelius the Sloth. Subscribe on Spotify or visit myweirdprompts.com.